Welcome to lecture number 4 of Geology 2017. We have been talking about a number of things, but mostly the relationship between tectonic processes, which were briefly really illustrated in the previous lecture, so lecture 3. And these tectonic processes are somewhat linked to a number of rock types. So today we are going to take another perspective and sort of look at how we can classify different rock types that are sort of belonging to that group we mentioned at the beginning of lecture 3, which is the group of the igneous rocks. So the focus really is obvious. We're going to discuss igneous rocks. We are going to review some of the previous ideas we had, such as the importance of silica, which are key criteria for the classification of igneous rocks. So why bothering with the classification? Classification is a necessary evil. It is difficult, to classify things, but somewhat we need to be able to communicate with geologists or engineers and have sort of a common ground where we have those interesting discussions and we can derive important knowledge. So an engineer needs to be able to recognize, for example, a carbonate formation. And this is from the perspective of the problem we discussed in the first lecture of selecting geomaterials that will be used for the construction. For example, we know that carbonatic material is particularly competent and it's very good to use as a material, as a geomaterial that supports a road work. So if you construct a road, quite often you will lay a layer of sediment, which could be sand or gravels that have a carbonatic composition. So that's quite handy to know. And so you'll need to understand what a carbonate is, or for example a limestone is. And so limestone material is usually a rock that has a mineralogy that is represented for its entirety of calcium carbonate. So this type of knowledge is key, and quite often geologists have been sort of reluctant to adopt a common terminologies, and even here in Sudbury, or actually in the different mining camps that we have all around the sort of northern Canada, we ended up having communities developing their own nomenclature, which can be thought as an incorrect really way of classifying rocks, because it limits the reach that these classifications can have in the geological and engineering communities. And because of this regionality issue with classifications, the International Union of Geological Sciences, which was founded, I think, in the beginning of the 60s, had this strong idea of defining classifications for rocks that presented what is a common language, so that we could share across different communities the same terminology, basically. So being able to communicate and understand what each other are referring to when they are discussing a particular type of rock, it's critical. And this is really at the foundation of this lecture. We want to find the common ground so that among your colleagues, among the engineering community, and again the geology community, you will be well positioned to understand what the discussion is about. So if we are discussing, for example, about a mantle rock like a peridotite, you will understand straight away that we are talking about a relatively competent rock that is dominated by olivine and pyroxene. And this is just to make a simple example. Okay, so as soon as you can place a proper name to a rock, you will usually know straight away what kind of mineralogy is in the rock. And this has implications for an engineer from the point of view of understanding the geomechanical properties of that rock. So you will understand that the peridotite is quite competent and it's a strong, relatively strong material because of its olivine content, because we know that olivine is a very hard mineral from lecture 2. So we reviewed that, and we know that we are very close to quartz when we are dealing with olivine. And so that's handy to know in terms of establishing the geomechanical properties of that rock. So the constituents of igneous rocks are at the basis of these classifications, although the Hughes standard classification commonly imposes that we refer to minerals. So quite often the mechanical properties of a rock are linked to the mineralogy, and this is rendered obvious why people have tried to classify things based on what is called the modal mineralogy of the rock. However, in certain instances, it is challenging to just use the mineralogy, and so we look at usually the major oxides and minor oxide composition to establish the rock name. And so we will look at the composition in terms of chemical elements. So if we give a definition really of igneous rocks, we could say that an igneous rock is essentially the result of the solidification of a silicate magma. And this means that silica is one of the dominant components. So chemically, 99% of all silicate magmas will be composed of major and minor oxides, and this includes silica, titanium, aluminum, iron, manganese, and all those more alkaline elements such as sodium and potassium. Together with these oxides, there will be what is called a volatile component. We mentioned it in previous lectures. So there is a certain amount of water, carbon dioxide, and other gases like sulfur and halogen that will be part of this composition. There are also other trace quantities. So we discussed, about trace elements such as zirconium, for example, or the rare earth elements that are commonly found in these accessory minerals we mentioned, such as spinels. So the spinels family will have trace amounts of these minerals. So you will have cases in which you have traces of things like uranium within some minerals such as monazite, which will be trace elements, or zircons themselves can host actually zirconium together with traces of uranium. So there are dominantly some minerals like quartz, feldspars that will be the ones that are really critical for the classification of the rocks, and these are the ones that contain the majority of the silica and also the other major elements. So we tend to discriminate between major, minor elements depending on the modal proportions that they have in the rocks. So since feldspar is quite abundant, potassium would be a major element in this context. If we are talking about potassium feldspar. So from this it may seem that you need to know a large number of minerals because of the complexity of the composition of these magmas, but as I stated, the fact that some minerals are the most dominant and abundant, this I think reflects also on the microscopic recognition of those minerals. So the majority of the classifications that we are going to review relies on these major minerals. And so minerals that contain iron, that contain magnesium, and sodium, potassium, and calcium will be the dominant one. So the plagioclase, the K-feldspar, and also the olvine, pyroxene, amphibole, those are the key minerals. If these are the key minerals, you can see them listed here. The straightaway distinction you can make is in terms of color, in particular going from white to black. You might have noticed that already in previous lectures. When we start to have more mafic components or ferromagnesium minerals, we tend to get darker rocks. When we have potassium-rich rocks, quartz-rich rocks, so at the end of the classification of Bowen in terms of crystallization series, rocks get whiter in color or pinkish in color if there is a lot of K-feldspar. So this translates really in those mafic and felsic assemblages we have discussed previously and their connection with tectonics. So subduction versus oceanic ridges and hotspots, which are mostly composed of mafic rocks or intermediate rocks. Okay, the common accessory minerals, we mentioned those, so the titanium, iron titanium oxides, sulfides, so like pyrite, apatite, and zircon. I mentioned them in the previous slides when I was talking about trace elements such as uranium. So, and sphene, when we talk about the spinels, we certainly have to deal also with these more titaniferous compositions. So in the Bowen sequence, you can see here the transition in the chemical compositions. It's also important for the classification of the rocks. So quite often highly fractionated rocks that contains trace minerals. So the spinels will be more titaniferous. Instead, the spinels that form really early are more characterized by refractory compositions. So we tend to have substitutions that prefer elements such as chromium that are highly compatible with the magma. Okay, so they will be the first to fractionate basically at relatively high temperatures. So we are revisiting some of these ideas, and it's important to remember that these will be your mafic minerals and these will be your felsic minerals. So these are white quite commonly or pink in color, and these are essentially going from greenish brown into black. All right, so that's a key distinction. These are usually quite dark in color, but they can assume also really interesting colors like red, green, especially if we are referring to, you know, the rubies or other gemstone quality spinels. And those, remember, are the ones that contain significant amounts of magnesium and aluminum. Silica, as I said before, is also critical for the differentiation between felsic, mafic and ultramafic rocks. So we go back to the last diagram we were discussing in the previous lecture. We can see percentages here, so remember the 45 break for the ultra basic, so everything that has less than 45% silica will be an ultramafic rock, so a peridotite for example. Then we go into basalts, so a basic rock. It's a mafic rock which has 55 to 52% silica, so a melanocratic rock. So we are introducing another way of calling these breaks, so melanocratic, mesocratic, so in the middle in terms of color, and leucocratic, which is essentially saying that it's light the color, whitish color for acid and felsic rocks with more than 65% of silica. So the content of silica is also related to the color of the rocks. Here is another example with another perspective, looking at the percentages of the mafic minerals. We often have charts of this type that give you an indication of color based on the percentage of mafic minerals present in the rock. So going from 10 to 17.5%, you see the dramatic change on the amount of white in this diagram. And so this would be an example of a melanocratic rock, and so that automatically means that we are between 67, actually 67 and 100% mafic minerals. So these terms are important. You should try to familiarize yourself with these, because I might actually ask you if a specimen is a leucocratic specimen or a mesocratic specimen. And for learning this, I will give you during the labs some assignments that sort of deal with the description of these rock types. Additional factors exist on the classification of rocks. We have briefly touched on those already. So if you remember the Bowen sequence, on the felsic side, we have a transition from plagioclase into K-feldspar progressively through fractionation. So not only the composition of the plagioclase changes, we saw that it goes from calcium-rich plagioclases to more alkaline plagioclases to end up into K-feldspar. And so that's a good indication of the level of fractionation, but also it does have implications for the color. Quite often you go from a completely white mineralogy, so very leucocratic, into a more pinkish mineralogy when you have abundance of K-feldspar, or a mixed case if you are at an intermediate stage of fractionation. So a combination of plagioclase and K-feldspar will be visible, and usually a decrease in the amount of silica is also evident. The olivine, pyroxene and amphibole content are also important guides. This is particularly key for intermediate rocks, which usually have a kick in the amphibole content. So if you have a lot of visible amphibole in a rock, that could be, for example, a volcanic rock such as an andesite, well, that's a good way of classifying the andesite. So if you can recognize a good percentage of amphibole in the rock, that's a good sign. The same is true for igneous rocks like tonalites. Usually they will have quite a bit of amphibole in them, and it's useful for the identification and distinction of those tonalites from granitic rocks. But yeah, we are going to see more of these, so you will learn really this. We saw that third point already when we were discussing about leucitites, so examples of rocks that are relatively low in silica, so low that they are struggling to make up feldspar, and so they develop those feldspatoids. So evidence of leucite or nepheline in a rock is sufficient to sort of distinguish rock that are relatively low in silica, and so quite often they move towards the mafic assemblages. So Strachan was among the first that dealt as part of the Hughes effort with this problem, and he came out with this QAPF diagram, which is essentially a summary of this discussion we were having with respect to comparing color with mineralogy in a rock. Why color is so important? It's because you are supposed to use color to recognize rocks. So in reality, color will be not the exclusive thing. You're going to use also your eyes to recognize peculiar textures, and of course to recognize the minerals themselves if you are able to do so. And this is quite obvious for igneous rocks that are intrusive rocks. For those ones, usually the textures of the rock and the mineralogy is really macroscopically visible, and so it's easy to identify quartz, identify alkali feldspars, plagioclase. So quite often people tend to draw these triangular diagrams. We will see many of them in this course, and quite often you can simply explain these as a percentage of what is called a modal mineralogy. So we have end member compositions. So if I have a rock that is dominated by alkali feldspar, let's say we have more than 90% alkali feldspar present, or orthoclase, we would be placing the rock in this space, so in this corner here. Instead, if I have a quartzite, so a rock that is dominated as more than 90% quartz, it will be on this top part here. And also if we have another rock that is dominated by anorthite, so a plagioclase, calcium plagioclase, it would sit here in this corner. So it's very easy to then make mixing of things, and so you would expect I could ask you, what do you think is the position in this diagram of a rock that has a compromise composition? So a compromise means a mix between, for example, quartz and plagioclase. So if the rock has 50% quartz and 50% plagioclase, I would place it right here because there is no alkali feldspar in the rock, so it's going to be sitting in this location. But as soon as you have three components, well, you need to be right in the middle of the triangle. Maybe if you have the same percentage of composition, so roughly 33.3% of the three minerals we are discussing for this particular triangle. What happens if you have some feldspatoids like leucite? Well, you would be pushing things down here because you start to have some percentages as soon as you move across this line of feldspatoids. So if it's only 50-50 between alkali feldspar and feldspatoids, I would be right here, and then I can move in here as soon as I increase the amount of plagioclase. So if I have a mixture of 50-50 between plagioclase and 50-50 between alkali feldspar and feldspatoids, well, I'm right in the middle of this triangle. So it's very simple to use these triangular diagrams, which represents different mineralogy, to essentially classify these rocks, because as soon as you are in one of these domains, automatically you can add a label or a name to these rocks. What is the limitation in this case for the Strachan diagram? So when he developed this diagram, he didn't really think that much about mafic minerals. And in fact, mafic and accessory minerals are not really considered in this diagram. But yeah, this is, still a good guide to understand the degree of fractionation of these rocks, because you have the quartz here, so we go from highly siliceous and fractionated rocks to relatively unfractionated examples where we have very little quartz. So that's another key aspect, and also the transition. So if you think in terms of Bowen fractionation, going from plagioclase to, alkali rich feldspars, it's certainly a good way of measuring fractionation in a rock. And so by looking at this, you know the stage of fractionation, and you can relate back also to the mafic minerals, because we know that when the rock is highly fractionated, we will be on this side, and with the K-feldspar we will have, for example, some biotite, which is a good example of a ferromagnesium mineral, so a mineral that you commonly find in a mafic rock. Okay. Other cases, mafic minerals could be also present in here. So quite often when you have lots of plagioclase, you will end up with a significant amount of pyroxene and also amphibole in the rock, in contrast to the biotite. So less fractionated, more pyroxene rich rocks, instead of having those phyllosilicates. Okay, this is sort of a nice introduction, but what about adding those labels? So we end up with the Strachansen diagram, that is the one that officially geologists use to identify the nomenclature of rocks, and certainly it's important to realize the complexity here. So these triangles can be subdivided in different sectors, and this will represent ranges really of model proportions. Okay, so these are percentages of mineral, of a particular mineral contained in the rock. What does this mean? If we take the most simple example, the granite, okay, so when do you have a granite? Granite usually will be classified as such if you have a composition that is between 20 and 60% quartz. Okay, so this is how you use this diagram. The more you move this way, the more you increase the percentage of quartz. In fact, in this domain, the quartzites will be rocks that have more than 90% quartz. The remaining 10%, it could be a mixture of plagioclase and alkali feldspar. So a rock that is slightly less enriched in quartz, so between 60 and 90% quartz, it will be usually a quartz-rich granitoid. So it's a granite with quartz, basically. And what's this? It's a granodiorite. So granodiorite is a rock that has a little bit more plagioclase, basically. And in particularly important is this 65% mark. So if you have more than 65% plagioclase, well, that's the case in which you call it a granodiorite. So if you see very little quartz in a granite, well, most likely it's either a tonalite or a granodiorite. Okay, and also, yes, remember, it's more a game between alkali feldspar and plagioclase. So a rock that is mostly white, it's more likely to be a granodiorite because of that, because you have less K-feldspar basically in the rock. This sort of is again clarified in this diagram, in which you see the proportions of minerals, and you start to see, we can go back to that discussion we were having about plutonic rocks, and we can see, that the granite usually have very abundant alkali feldspar, quite a bit of quartz, and then those highly fractionated phyllosilicates, so muscovite, biotite, and plagioclase, but just a little bit of that, as well as amphibole. So these three minerals will die off when you get more in a field of the mafic and ultramafic assemblages. So you will lose the amphibole, although this mineral still is available really in the gabbros. But yeah, when you're talking about a peridotite, so an ultramafic rock, you lose really the ability to have minerals that host water. Some more in-depth examples here. We are starting to look at the textures of the rocks. So you have some pictures here that illustrate some of the points I was trying to make about granites and granodiorites. So we have some examples here. So if we look at this picture here, this is an alkali feldspar granite. What does that mean? It's essentially a rock that would fall in this narrow field here, which means that you have between 20 and 60% quartz. But yes, this rock is dominated by alkali feldspar. It means 90% of the feldspars in this rock will be represented by alkali feldspar. Only 10% is plagioclase, and this is manifested by the fact that the rock is highly pinkish, mostly pinkish material, as you see. And these other white plugs that you can see in the rock are quartz. You can see they are more translucent, grayish in color, and that's a good indication that you are dealing with quartz, especially if you test this rock with acid and it doesn't fizz, so there is no carbonate here. And also if you test with the knife and you cannot really scratch these minerals with the knife or a pin nail, well, you will be most likely with a mineral that is quite hard, and it's likely to be quartz. Okay, the other mineral that is visible in this specimen are more darker plugs. Quite often these, if they are scratched by the copper coin, they will be biotites. If not, they can be amphibole. Okay, so some of the granite will contain quite a bit of amphibole and biotite. So that's your alkali feldspar granite, so a rock dominated by K-feldspars essentially, and quartz. What about the granite? Granite will lose some of the feldspar and replace it either with quartz or plagioclase. And you see an example of what I was saying here. You start to have more mafic minerals as well, so you can see more black plugs of biotite, but also regions that are gray in color that are more representative of quartz. But surprisingly, you have also white, more less translucent and more cloudy crystals that are whitish in color, and these are your feldspars, but most likely plagioclase instead of K-feldspar, because of the fact that the K-feldspar here is more represented by these pinkish plugs. So there are pinkish and whitish feldspars, and so two trends here, really two compositions for the feldspars, which puts you right in the middle of this diagram, and so you would call the rock a granite because of that. And you see the mafics are also a key indicator as well. And in fact, if we move into a granodiorite, you clearly see that this rock has even more mafic component to it, so it's becoming darker. So you could start to say that the proportion of dark minerals is very close to the amount of white minerals, and you have lost the pinkish K-feldspar in this rock, which is a good guide to help you classifying the rock, calling it a granodiorite. So we also lose, the well evident abundance of quartz, because the plagioclase is really abundant in this rock. So we have quite a bit of plagioclase that mixed with the quartz, so it's more difficult to differentiate. I guess one key aspect here would be to search for phyllosilicates. So if this is a less fractionated rock, you would have also less biotite and less muscovite present in this rock. Although it's important to flag the fact that when we have a rock that starts to be really dominated by plagioclase, we should call it a tonalite, and quite often tonalites have a significant amount of amphibole in them. So you can see here are some of the sections of elongated amphiboles, which can be also helpful for the discrimination. So if the mafics become dominated by amphibole, we are in a situation in which the rock becomes more an intermediate rock, and so it will be most likely a gabbro or a tonalite. Well, we can move to the next slide. Actually, I forgot to mention that here you have another style of classification that can be helpful, and you can see the percentage of mafic minerals. So quite often you go from very low percentages for the alkali-rich rocks down to the tonalites that have, on the order of 20 to 30% mafic minerals, which can be mixed, with the granodiorite. But the difference here, as I stated earlier, is really a question of the proportion of plagioclase in the rocks. So the tonalite is dominated, by plagioclase between 90 and 100%. So it's a bit, this diagram is a bit repeating what I was discussing in terms of composition of these rocks. But you can see that macroscopically, if you look carefully, you will be definitely able by visual inspection to discriminate between the granite group and the granodiorite and tonalite group, for sure. Moving further into more mafic assemblages, so less fractionated rocks, we can move down to this interval of the diagram. So the Stracasian that has composition in terms of quartz abundance that is inferior to 20%. So if we have less than 20% quartz, and we sort of have a range that goes from rocks that are completely devoid of quartz to rocks that have on the order of 5% really quartz. This is another important distinction that separates, for example, the quartz cyanites from cyanites. So keep in mind that this field also contains a further subdivision that is this 5% mark in terms of quartz content. Good. So if we look at this rock here, we can see that the mafics are more abundant, and we still have this pinkish K-feldspar that is quite distinctive. Okay, so if we cannot really see any really abundant quartz, quite often we have to attribute this rock to something that has less than 20% quartz. So it looks very much similar to a granite or a K-feldspar rich granite, so the alkali feldspar granite. But the fact that there is no evidence of abundant quartz, it's actually placing this rock in the cyanite group. And in this particular case, we almost see that it's devoid of quartz, because these plugs here most likely represents plagioclase. But yes, there might be a small percentage of quartz, like in this domain, so the more grayish sort of minerals in here, but still very little percentage. So cyanite, it's more appropriate. Monzonite will move further down this way, so we change some of these K-feldspar into plagioclase, more abundant plagioclase here, so less pink in this rock, more mafics as well. So you have interstitial mafics, which could be amphibole or pyroxene, and that's enough really to argue for a monzonite. And then you move into dioritic composition, so you lose the pink completely, and you are in this space in which you have a rock that is dominated as more than 65% plagioclase, and then have a combination of amphibole and pyroxene in its matrix, but it's still quite white. Usually when the proportion of mafics exceeds the amount of felsics, you have the same composition, so plagioclase and pyroxene with amphibole. You go into the gabbros, and then when all the amphibole is gone and you are left with just pyroxene, not much quartz really, and a situation in which olivine starts to dominate, you will end up with the compositions that are more dunitic, so a peridotite, or anorthositic if you are sort of reducing the amount of these materials, so the pyroxenes, and you have labradoritic compositions of your plagioclase. So a rock dominated by plagioclase, it's a rock that could be termed an anorthosite. Here is a summary of this discussion. Again, we have this field in which anorthosite rocks have really little content in terms of mafics, so we have between 0 and 30% for anorthositic gabbros, but for the anorthosite it's 0-10. Okay, so this rock has only 10% maximum of mafic minerals, and it's dominated by plagioclase. So the anorthosites contain essentially mostly plagioclase. Despite this, they can be quite dark, but often the iridescence of the anorthosite crystals of plagioclase is quite evident, and it's almost metallic, and gives you a straightaway answer in terms of identifying this particular rock type. So hopefully this has given you a spectrum of compositions and textures, and you can see how the color is instrumental in distinguishing rocks that are abundant in K-feldspars from rocks that are plagioclase rich, like Diorites, as well as the increase in olivine and also pyroxene in transitions that go from anorthosites into dunites. So the Hughes classification is quite handy, but there are actually two classification diagrams, not just one, and one is used for the extrusive rocks, like this example here. So the volcanic rocks quite often have a different nomenclature. Even if the composition is very similar, they have a completely different texture, and this is why we refer to them with a different nomenclature. And they also have a different location, because these are more superficial rocks or subaerial rocks that form at normal pressure temperature condition, and this is process that often leads to quenching, and because of that you have a range of microcrystalline textures that will form in these rocks, as we have discussed in the previous lecture. So what does that mean? It means that the rocks will usually have a less evident mineralogy. That's the key idea. So if you take, for example, a granite equivalent such as a rhyolite, so same composition as a granite. So if you remember, we mentioned that the composition is 2060 in terms of range of quartz content for a granite. So it will be the same for a rhyolite. But at the same time, so the rhyolite contain also abundant K-feldspar. In fact, this example is a good one because it's quite pinkish. It can be helpful. You will see small crystals of K-feldspars many times in rhyolites, although they're smaller and they can be often immersed in a microcrystalline matrix. So you will see isolated crystals which are commonly defined as phenocrysts. So remember, when we see minerals that are larger than the matrix of the rock and they appear well distinct with well-defined habit, they are commonly termed as phenocrysts in volcanic rocks. So for example, here we have examples of phenocrysts in this dacite, and this will be likely plagioclase. So you have several phenocrysts in white in a matrix that is more dark reddish, and it's likely a paste that is solidified very rapidly, and it's quite glassy because of the dark color. So that's the example really of a dacite. If we look at the position of a dacite, is right in this domain. So if you have quite a bit of quartz, the rock will look glassy, dark, and this is also the result of the fact that in this rock you will have a composition that is similar to a basalt or an andesite, so an intermediate rock which has quite often more quartz than basalts and andesites, but still have quite a bit of mafics in there. So pyroxene will be abundant also in this rock. So a rock dominated by plagioclase and pyroxene, but has also quite a bit of quartz, will be your dacite. Here you have other examples of felsic rocks like rhyolites, which can have more fragmental textures. So because these are commonly pyroclastic products, so related to the ejection from a volcano, you can have mixtures of the lava itself together with other things. So ejecta fragments of the crater, for example, could be part of the rock during cementation or deposition of a rhyolite. Often these rocks exhibit stratification, or complex flow-banded rhyolites like this will show wiggly, sort of folded stratifications that are a good indication of the environment of formation. So subaerial rocks quite often have stratification that indicates different periods of deposition of these silica-rich sediments. So you can resediment even a rhyolitic ejecta, because if they are cinerites, quite often they will be very siliceous, glassy, so similar compositions of between 20 and 60%. And so you can call them rhyolites because of their composition, but they have a very complex texture, which is the result of the accumulation of cinerites. If the quantity of silica is extremely high, so we are in this field up here with 90% or more quartz, we commonly have, because of the quenching and quite rapid solidification, in subaerial condition, we tend to form this volcanic glass, which will be amorphous, very hard like quartz, but usually exhibiting classical conchoidal or curved fracturing, which can be very sharp. So you can cut yourself with a volcanic glass of this type, but also the color is quite distinctive. They are usually very dark in color, so black. Rocks that are also part of these ejecta are quite often pumices, which will be distinguished by their weight. They're very light and porous. So you can see a lot of cavities in this rock, which are linked to the subaerial condition in which they form, and these bubbles are linked to the degassing during cooling, rapid cooling of this fragment of pumice. Moving to the more mafic assemblages, we can sort of see clearly a dramatic change in color. We lose the pinkish and we go into things that have compositions that are either more rich in plagioclase or even foids, so foidites here. So rocks that are dominated by foids could be like these, in which we have very large crystals of leucite recognizable in the rock by their symmetry, so they form these nice dodecahedrons. Or you might have phenocrysts of amphibole that dominate the matrix of a volcanic rock of this type, and so you start to think that this could be an andesite because of that intermediate composition. If you push things further, you get the rock really dark, black in color, so a rock dominated by a pyroxene and often plagioclase will be your basalt. So we have usually less than 20% quartz in these rocks, and then here we move into more intermediate rocks, so the trachytes and latites, which usually have a combination of plagioclase and K-feldspar as sort of key indicator minerals. And finally, you have cases that are more extreme, like olivine or picritic basalts, so olivine-rich basalts, which usually are derived from ultramafic magmas. So hopefully this has given you an overview of rocks that are more volcanic. You can distinguish them because they have these classical porphyric textures in which you have crowded textures represented by felsic or mafic minerals and a microcrystalline matrix that supports these crystals, which are isolated within a matrix, or sometimes they can be crowded, and sort of you will recognize crystals with the edges that touch themselves, like in this example here of this trachyte. But here these crystals are more floating, and so they float in this microcrystalline matrix, which usually have a similar composition. So there will be also amphibole in this matrix together with pyroxene and likely plagioclase. Same is true here, but we can see also that this lava is vesicular, so we have cavities similar to the pumice that indicates subaerial condition of crystallization with significant degassing, because if you have low pressure you tend to liberate the gases. So quite often when we compare intrusives with extrusives that have similar composition, we refer to the concept of heteromorphism. So we could compare an andesite with a diorite to increase complexity of this discussion, and we would see that there are marked differences. So It's true that the chemical composition of the rock is the same, but often you get different mineralogy as well. So the plutonic form usually, so the diorites usually contain quartz, amphiboles, or micas, so muscovite, whereas your andesite is more represented by pyroxene and glass quite often. So you essentially lose the quartz and replace it with amorphous varieties such as volcanic glass or obsidians. So diorites will usually contain visible quartz. That's the key distinction. But in most andesites, this is concealed in the fine-grained matrix. So it's mostly a difference that is a textural difference. What geologists found, though, is that most of the rocks can be classified using the Hughes classification, but many times igneous rocks will require accurate estimates of the model composition, and this can be difficult in some cases. It's difficult for volcanic rocks to establish, the model mineralogy, and this is quite obvious because these rocks are fine-grained in their matrix. As I said, they're microcrystalline, and so you don't really have capacity to estimate the percentage of a particular mineral, which renders them challenging to use the classification of Strachan, which is based on proportions of minerals. So how do you solve this problem? I guess you have to rely on other classifications, So the key classification is the total alkali versus silica classification. This diagram is somewhat a better way of addressing the classification of volcanic rocks, but in this case, rather than using the mineralogy, it's using percentages of oxides. So we use the percentage of silica versus the addition of two oxides, the sodium and potassium. So the alkali are these guys here, and they will have weight percentages that goes from 1 to 13 or more, and that's quite handy to distinguish alkaline series from subalkaline series down here. And so quite often we are able to differentiate three main trends in this diagram. So you have essentially trends that are calcalines or represented by rocks that have a certain alkalinity, and rather subalkaline trends that are more tholeiitic trends. Other things that we can use are also key boundaries that are based on the relationship between the alkalis, so the proportion of the alkalis, so sodium versus potassium in this case. So if we look, at a trachybasalt, which is composed either of howellite or potassic trachybasalts, in that particular case, the distinction in terms of abundance of potassium versus sodium is critical. So the same is for these basaltic trachyandesites, and for trachyandesites you can make a similar distinction, although this is, I think, too sophisticated for this discussion at this stage. I would rely dominantly on this diagram really, and look at this change in silica content as a guide in terms of level of fractionation. So on this side you have the less fractionated assemblages, and here you have the more evolved magmas that are more siliceous in content. And in fact you go from basalts here into the rhyolite field up here, and a shift across these three trends goes, you know, from this series that is the classical series of the calc-alkaline group. So you go from basalts to andesites, and then you have this other series that is more the alkaline or peralkaline series, which is represented by the basanites up to tephrites and phonolites. And right in the middle, you have your trachytes that dominate sort of an intermediate trend in terms of alkalinity. So the alkalinity is intermediate in this middle trend. Similarly, these trends can be sort of well represented here, so same type of classification here, just simplified. So you will have the alkaline series, the mid-alkaline and subalkaline series, as I was mentioning. And these will correspond really to this main sequence of igneous rocks, which can be related to tectonics. So the alkali content control the series in which you are, and the silica level instead will control the differentiation. So these are powerful tools that usually petrologists will use to infer the origin and tectonic setting in which the magmatic event occurred or are occurring. And we can make the Hawaiian examples in which we have those picritic compositions and go through these series that are actually subalkalines, I think. Another example here with other ratios. Sometimes we can calculate ratios of oxides, and this will give us other ways of differentiating rocks. In this case, we are comparing essentially the alkalis, so sodium and potassium against aluminum, and down here we have also this calcium. So we add calcium as a dominant factor for the differentiation. So of course, if you increase the denominator here, so the calcium, sodium, potassium index, well, you would be up in this range because the ratio value will increase. So between 0.6 and 2.6. So rocks that are extremely rich in calcium, sodium, potassium will fall in this domain. And so we can distinguish, you know, alkaline rocks like rhyolites, trachytes, and phonolites will be distinguished, and you can see trends here in which you go from your more mafic assemblages, so basaltic rocks, to subalkalic basalts, into things that are more progressively more alkalic. And so you can distinguish here a boundary that will separate essentially rocks that are relatively devoid of aluminum and alkalis from peraluminous and peralkaline rocks, which would be your rhyolites and your phonolites, respectively. So these trends are related to the incorporation of alkaline metals again. Usually these are sourced from the crust and require some degree of assimilation of the country rocks. So these diagrams have a tectonic implication. We saw that when we have thicker crust in subduction zones, quite often we have partial melting that takes place in the upper levels of the crust, which leads to increase in alkalinity. And so silica and aluminium and alkali will be the main components of highly differentiated crust, hence this progressive enrichment that we see. So plotting a series of samples in a chart of this type can provide insight on the type of tectonic setting where the magmatism occurred. So phonolites of the Canary Islands, for example, are plume-related magmatism on an oceanic crust setting. In this context, very low contamination would occur, leading to low aluminum contents. The other way around would be for the Andes. So in Chile, for example, some of the magmatism or magmatic series that we will observe will be definitely, on those fields of peralkalines or peraluminous rocks. And here we have other diagrams that look at transitions from basalt to rhyolite and to trachyte. So key minerals in this case are highlighted in these other diagrams. So we have differentiation index versus mineral abundance in percentages. And so how does this work if you are moving from a picrobasalt, so an olivinic basalt, and progressively increase the fractionation, so the differentiation, we go towards rocks that have more free quartz. So these rocks don't have any quartz, these are free quartz, which is an indication of the amount of silica. So if a rock is saturated in silica, it will produce free quartz. And you can see also this domain of alkali feldspar, which broadens progressively, and you shrink these fields of plagioclase, augites, and estatites, which you should remember these are pyroxenes, and the olivine here is disappearing even earlier than these pyroxenes. And then at the bottom you have these iron titanium oxides, so the spinels. We remember that we increase the chromium while we fractionate these rocks, as well as titanium. So iron titanium oxides will tend to sort of be substituted with amphibole, because these are trace elements. On this other side you have the subalkaline series, so very similar concept, but the difference is the abundance of quartz, which dramatically change the volume of alkali feldspar that is present in these rocks. So these are more quartz rich rocks, and so because of that you go from picrobasalts to basalts into andesites, dacites, and rhyolites. So rhyolites will be definitely more fractionated if compared to trachytes, and the result is rocks that have quite a bit more water as well. So you have amphibole and biotite that dominates the highly differentiated assemblages, and so you sharply decrease the amount of iron titanium oxides because of that. So the mineralogy really is a response of these fractionation trends, which will depend on the alkalinity of the rocks and the series that they belong to. We start to think now about rocks that are more out of those first three groups. So if you remember, we had 4 key groups of igneous rocks, so rocks that are felsic, mafic, and intermediate, and then ultramafic rocks. So we are starting to talk about these ultramafic rocks now. So the QAPF, of course, for these has very limited applicability, because, as I stated, one of the limitations for the Strakhazen diagram is the fact that it's based on felsic minerals. Because of that, we have a separate ternary diagram that is essentially evaluating the relative abundances of plagioclase, olivine, and pyroxene. So you need to look at the mineralogy of your rocks for their classification, since a ultramafic rock is dominated by these 3 minerals. It makes sense to use model proportions for these 3. And so we have a different nomenclature for rocks that are ultramafic and usually have, compositions that are dominated, for example, by plagioclase. I mentioned that before when we were looking at some initial examples of igneous rocks and volcanic rocks. And so we distinguished plutonic rocks such as Andesites that have more than 90% plagioclase. The other end member are the pyroxenites. By the name, you guess that they have more than 90% pyroxene. And then we find the rock that is classically green in color that we mentioned many times, the one that contain peridot variety of olivine, and those are the dunites, which have no more than 90% olivine basically. What if we have like 50-50 end members? So if we go in this location here, we will talk about gabbro-norites. So gabbros and norites usually are rocks that are poor in olivine, so they have less than 5% olivine, but they have 50-50 between pyroxene and plagioclase. Instead, if you move here, you have the troctolites. Troctolites are rocks that are relatively poor in pyroxene. They will be quite leucocratic actually because of that. And often you have a mixture between plagioclase and olivine, so they are still quite greenish in color. We will see some example later. In the middle you have your olivine gabbros and olivine norites, so the mixture of the three sort of end members, and down here usually you have plagioclase bearing ultramafic rocks that sort of dominates this plagioclase poor end member. So these will be rocks that are quite dark in color. Usually a pyroxenite is completely black and the dunite is completely green. So that's basically it for these minerals and key rock types. I would say that the color of these rocks, the anorthosite, is usually leucocratic. Then you go into mesocratic rocks and melanocratic rocks when you have that they're dominated by pyroxene and olivine. Some example here of the texture of these rocks. If you remember, we looked at the anorthosite already, so this metallic luster of the perlaceous luster of the plagioclase is quite unique, so it will shine quite a bit. And then you have on this side your gabbros and norites, so you have a diorite or a leucogabbro. In here, we remember that diorites have a kick in quartz, usually a little bit of quartz, but yeah, dominantly I have plagioclase and pyroxene. But here, you move down and increase the amount of black or darker phenocrysts, and so you have that the rock becomes dominated by the pyroxene until you end up into a pyroxenite, which is almost devoid of plagioclase and olivine. On this side, instead, we get rid of the pyroxene and we see clearly the difference. So this rock is much more leucocratic. The white domains are represented by plagioclase, and these more brownish domains or yellowish are olivine crystals. And down here, your dunite, which is classically peridot green, and they have also small phenocrysts of pyroxene. We have usually two varieties of pyroxene. One is black, so your augites, and one is greenish, dark greenish in color, which is your diopside. So the calcium pyroxene can be found in this variety of dunites. Other classifications to increase the complexity use pretty much the same principles of the Bowen sequence. So we have less fractionated Diorites with orthopyroxene and more fractionated gabbros and anorthosites that contain clinopyroxene, basically. So rocks that are fractionated will have a particular type of pyroxene, and you can see it in here. So we tend to have that we move from these classifications that are based on the mineralogy into the substitution on a particular mineral, which could be either the amphibole or the pyroxene. So in this case, we talk about orthopyroxene Diorites and clinopyroxene gabbros, for example, or plagioclase bearing pyroxenites for this field down here. But yeah, certainly this separation is quite useful for the distinction of Diorites. So if you find a lot of orthopyroxene in a rock, well, in that case, it's more likely to be an diorite. If there is mostly clinopyroxene, it will be most likely a gabbro. So that can be helpful. So with plagioclase, orthopyroxene, and amphibole as a criteria, you can sort of move into classifications that are relying rather on this change or transition between pyroxene and hornblende. So we have, plagioclase bearing hornblende pyroxenites or plagioclase bearing pyroxene hornblendites. So we talk about pyroxenites versus hornblendites, which complicates things even further, and in this particular case you will need to quite often to cut thin sections to be able to actually differentiate between the proportions of amphibole versus pyroxene, which is a bit sort of too much for this course, but is certainly important to keep in mind that these are other examples in which the mineralogy becomes instrumental in the distinction of different types of peridotites in this particular case. Other ways in which you classify, similarly to volcanic rocks, we can rely on the chemistry. So we could use chemistry to classify ultramafic rocks, and so an important example is here with different names really depending on the composition. So we're going to have just a tour of these different rocks and what it means in terms of oxide content really. So these numbers reflect essentially the percentages of oxides. So if we start with the top one, we look at the silica content, we can see here that this is pretty much similar across all the ultramafic rocks. If you remember, the key classification in terms of silica percentage is the break of 45%. So everything that has less than 45% is usually thought as an ultramafic rock. So we are pretty much close to that cutoff. But yeah, if we look at the other elements, for example, aluminum should follow a similar pattern, but we do see a dramatic change here. So if we compare a dunite with a picrobasalt, we can see a major distinction. So 10 times more aluminum content in a picrobasalt if compared to a dunite. So certainly ultramafic rocks will have less aluminum if compared to basalts, and so that's a key distinction that is quite helpful. So the aluminum content, the iron stays pretty much the same, exception for these asburgites. Again, we have two oxidation states for iron, so we could consider total iron or move to other things that I think are more relevant. So magnesium, for example, is quite relevant. We saw that ultramafic rocks tend to have quite a bit more magnesium if compared to basalts, which are mafic rocks. Is that true? And the answer is definitely yes. You can see major difference between a dunite, which is a peridotite, and a picrobasalt, which is roughly half in terms of magnesium content. Calcium is also helpful, so usually the alkalinity of the rock will be higher if it's more fractionated, so more primitive magmas, such as the one that form peridotites, will have relatively low alkalinity, and you can see the clear distinction here. The picrobasalt has much more calcium, for example, and definitely more sodium, and yeah, very much like almost 50 times more in terms of potassium. So definitely alkalinity, silica content, magnesium content are the key ingredients, I think, to differentiate the different types of ultramafic rocks. So we will see some examples of these rocks now to clarify their macroscopic distinctions. But you see here a summary between dunite and basalt, the distinction, so the alkali, the magnesium, the aluminum content, and also the volatiles. I forgot to talk about volatiles. So you have down here parameters, so the CO2 content, which certainly is decreasing if compared between peridotites and basalts. So we have seen a number of ultramafic rocks that have sort of a variety of chemical compositions. One key aspect of these, let's say, standard ultramafic rocks is their alkalinity. So they tend to have relatively low alkalis. And this represents a problem for the classifications that we have reviewed so far, because most of the classification assumes that you increase potassium, for example, with fractionation. And because of this, we have to discuss in this final part of this lecture a set of special igneous rocks. And these rocks are essentially violating this rule. So they tend to be ultrapotassic rocks, and they tend to have this ultramafic characteristic of, for example, having elevated contents in magnesium and being melanocratic rocks that are dominated by either olivine or pyroxene, but they have unusual mineralogy as well. So if we review some of these rocks, we also need to look at the processes that led to the formation of these rock types, which are quite unique, and they will influence, because of that, the composition of the rock and make it unique as well. So one example are the cumulate rocks. These are including ferromagnesium cumulates, feldspar cumulates, and feldspatite cumulates. We have mentioned cumulates in a variety of environments, but you have to think of cumulates as either part of a process of fractionation within a magmatic chamber, or they could be related to a lava flow. So we have seen that some of the rocks are classified as volcanics, and these volcanics can include ejecta and lava flows. So we will discuss this more in detail, but keep in mind that cumulates can form within a magmatic chamber as well as in a lava flow. We will see and discuss some examples of these. The other type of rocks are the high magnesium rocks, so the boninites, the comodites, mamikites and picrites, and these are example of lavas like komatites that we will consider. Other igneous looking rocks, so charnochitic rocks, eclogites, glimmerites, gneiss and migmatites. I think in this course we'll focus on eclogites and migmatites, so we will have some discussion about these rocks, but when we will deal with the metamorphic part of the course, so we can leave them for the moment. And I think we will focus really in this final part of the lecture on the cumulates, so the komatites, and also on the lamprophyric rocks. And this is a bit old as a classification, because now lamprophyres are sort of separated from kimberlites and lamproites. So let's just focus on kimberlites and lamproites for the sake of simplicity. The last group is represented by mantle rocks. So we will see also processes that look at the, let's say, metasomatism of the mantle, and the processes that involve partial melting of mantle. These are cases that involve mineralogical changes and transitions in the mantle, and so this results in usually in depleted mantle rocks or more fertile mantle rocks in terms of availability, for example, of fluids. So this part of these particular rocks will be discussed in other lectures, mostly dealing with ophiolitic sequences, because it's there that we find these type of processes together. I think with also the boninite, we will discuss boninites in ophiolitic complexes as well, or in a mid-oceanic ridge environment. So when we discuss more in depth those environments where we have close interaction with ultramafic rocks and essentially remelting of the mantle. So if we start from the first group, we have the cumulates. We are revisiting the concept we discussed already in a magmatic chamber. Usually you have crystallization that takes place with the nucleation of minerals. This could be either mafic or felsic minerals, and they will have a density that could be either higher or lower than the magma. If it's lower, quite often the minerals that are usually felsic will float on the top of the chamber. The other case is when they have a denser they are denser materials if compared to the magma, so they will drop and accumulate at the bottom of the magmatic chamber. So these two processes usually leads to, for example, chromites or dunites can form because of the accumulation of abundant olivine. So when you have more than 90% olivine, we saw that we are dealing with a dunite. But yeah, it's important to realize that this could be the result of the accumulation really of silicates of a particular type of silicate, and these sort of crowded rocks will be the result of this type of differentiation. So usually, as I said before, they form by either settling or rising of minerals at the bottom or top of a magmatic chamber. So that's important to know as a process of formation for these particular rocks. So remember, you can form iron-rich cumulates like magnetites. So if you think of large igneous provinces such as the Bushwell complex, you will form chromatites, magnetites layers, and so all these rock types take essentially the name from the most abundant cumulate that is characterizing that igneous layer of either oxides or sulfides, because you can form also PGE, so platinoid layers will be found in association with chromites, for example, in the Bushwell. So most cumulates will be either ultramafic or anorthositic in composition, so depending if you have mafic minerals as the dominant, so the chromites, for example, or anorthositic if they are feldspar dominated. So if you have dominantly plagioclase like labradorites, we saw already some example of that, so you might form this sort of almost monomineralic rocks as a result of these processes, and so they take those peculiar names. Well, so there is a little bit of overlap with the ternary classification, but there will be exceptions like the chromites, in which you have to sort of take this process in consideration and classify the rock and give it a name based on its origin. Another example of cumulates is often found in relatively ancient magmas. So these were dominantly Archean to Proterozoic in age. And because of this, they have this key feature, which is the fact that they are lava flows that were relatively hot, so on the order of 1600 degrees. If you remember, I mentioned that the majority of the magmas will range between 700 up to 1200 degrees. So these were 400 degrees hotter lavas, and they form quite thick plateaus that were exceeding several tens of meters. So quite often these plateaus are relatively thick, as I said, and so they imply slow cooling and differential cooling, usually on magma flows of this type. And so also they have ultramafic compositions, so they are extremely rich in magnesium and usually low in silica, potassium, and aluminum because of that, which is expected. But because of that, you tend to crystallize quite a bit of olivine, and it takes a quite unique habit, which is more bladed habit, and so you see these elongated crystals, which in this particular example have been severely altered. Usually these magnesium-rich rocks get chloritized or serpentinized, so it's difficult really to recognize easily the habit of the minerals, but you can certainly see these elongated crystals which take this particular name of spinifex texture. So the story goes that these crystals grow in sort of areas of these lavas that, or volumes of these lavas that are relatively shielded. So quite often when you have this type of lava flows, you form a crust on top, which is more glassy and partly olivinic, and subsequently in the deeper parts of the lava flow, you start to gradually cool the top part of the lava flow, and quite often you form this type of textures. So you have essentially a situation that is almost hypabyssal in a way, in which you have time to crystallize some of the main mineralogy, in this case olivine. Many times the spinific textures can be different depending on the depth, and it's usually separated by a B layer, so a basal layer that is represented by cumulates, similarly to the cumulates you find in a magmatic chamber, as we were discussing before. Although there has been significant debate about the formation of these cumulates, which is attributed to convective flows that tend to redistribute some of the mineralogy that crystallizes in the lava flow. But I think that's a bit too complex. It's rather important to give examples of really how these things looks like, and you can see here the bladed olivine crystals quite clearly, and they can be either iso-oriented or randomly oriented, like in this case, in which you have sort of some crystals that are oriented, let's say, almost parallel to this margin of the sample, and other will be orthogonal to the margin of this specimen. So you can recognize this structure in this diagram here, which is a cross section through a komatiite flow, which is a schematic really, but it gives you an understanding of the different types of spinifex. So the scale and the size of these crystals can vary significantly. Here we have examples on the order of few centimeters, which will be this top part, but sometimes the olivine can grow to the meter scale, and that would be this A3 layer. And then you have these B layers that are rather represented by more conventional cumulates. Another example of unique rock types are kimberlites. Kimberlites are usually porphyric, so they will have big phenocrysts or xenocrysts in this particular case, because they are derived from adjacent rocks. So for example, xenoliths could come from the crust, or also they could come from mantle. And so you see all these dark fragments and some green fragments in this sort of finer grain or microcrystalline matrix. So they are very similar to a porphyry, although this looks more like fragments rather than phenocrysts. And also they look very often quite rounded, which indicates that the margins of these potential fragments or crystals have been rounded by the energy of this process. And in fact, kimberlites originally discovered in South Africa, but also abundant in India, and even here in Canada, so in ancient cratons, essentially, even in Australia, in the Argyll district, they are quite abundant. They are often associated with areas that are relatively active and connect mantle to surface. So these are commonly resulting in volcanic activity and diatrems. The difference with a classical diatrem is the depth of sourcing of the material. Kimberlites usually form at significant depth, and so we are sourcing material directly from the mantle, and usually we are under a continental setting. So in intracratonic settings, often you form these kimberlite pipes that are quite narrow, on the order of few hundred meters, so between 100 and 500 meters. So many times erosion, since these are old cratons, you find pipes in relatively old rocks, so Archean rocks to Proterozoic rocks, and so you will get erosion taking away the top part of these calderas, and you are left with challenging discoveries of these pipes, which usually is based on prospection for relatively hard minerals that are found in the kimberlites. For example, this greenish mineral here could be the either an olivine or a pyroxene, so a diopside variety, usually chromium-rich. Diopside can be deep green and will be found in kimberlites. One key characteristic is this explosivity, which is often linked to degassing at depth of compositions that are essentially carbon rich, so CO2 rich. Some people argue that this is linked to subducting plates, so we are essentially reworking some of the carbonatic sequences, and dehydration leads to liberation of high quantities of CO2. Others are arguing that the CO2 is directly sourced from the mantle, and this is sort of still in debate. It's interesting to note that these, together with the lamproites, so kimberlites and lamproites, are rock types that, because the carbon, they can actually host, and they are economic for diamonds. So we were talking about South Africa, and in the Kimberley area many years ago, I think that was in the 60s, they identified a kimberlite pipe, and they were able to recover a huge diamond. If we think in terms of the unit of measurement, usually the diamond is measured for size, for sure, so big diamonds, but quite often you look at the weight of the diamond, and usually the unit of measurement is the carat, which is equated to roughly 0.2 grams. So 1 carat is going to be 0.2 grams. So in South Africa, they did find a very large diamond. It was roughly on the order of 86 carats, which, if we times by 0.2, it turns out that it was roughly on the order of 16 grams of diamond. So a diamond that could be a few centimeters in size. So of course, these are very rare findings. And this is why they render these gemstones quite valuable, so on the order of several $million. And because of that, they are highly sought. And this is why we are discussing kimberlites and lamproites, which are very similar in first place. So remember, kimberlites and lamproites, they can host diamonds, and they have these unique porphyric textures with a variety of minerals, but they contain also carbonates, the kimberlites specifically. The lamproites, you see, very similar, but quite often They have this unique appearance of micas, phlogopites. So you can see crystals in here of what I believe is a mica, and that would be likely a phlogopite, so a variety of biotite. And yes, these are still porphyric. You can see phenocryst or xenocryst in this rock, but a key distinction, I think, is the fact that usually you have little carbonate in these rock types. So there are some kimberlites that will have also micas, usually the type 2 kimberlites, but for sake of simplicity, let's assume that lamprophyres are quite unique because of this mineralogy and the fact that they are devoid of carbonate, which is one of the key aspects for the kimberlites. Another example here of lamproites, so we can revise the composition. So they are ultrapotassic, similar to the kimberlites, mantle-derived rocks, similarly, but they have low calcium, as you see here, and also low alkalis, but high potassium. So in this particular case, they're very similar to the kimberlites, and this is why they're difficult to distinguish. But these rocks usually don't have as much olivine. Usually you have high percentages of olivine in a kimberlite, which makes easier to distinguish them, and this is resulting also in a particular type of alteration. So you find quite a bit of serpentine in your kimberlites. So this lamproite from the late Cretaceous and located in Kansas is the last specimen that we review of these unique ultramafic rocks. What we're going to do now is to just review how to name your igneous rocks. And this is important because one of the assignments that we consider in this course will be devoted to the classification of a number of rocks, and this is based essentially on the Strachan diagrams, and so you have to be able to place the specimens in the ternary diagrams in an appropriate fashion. And this is why we are going to review a few slides about ternary diagrams and how we classify rocks again. So we will start by looking at the most basic rock classification, which is based on the silica content. So again, remember, these percentages are quite useful, but quite often if you want to classify a rock, you will use a ternary diagram like this. And so we're going to discuss really the nitty-gritty of how to use the percentages of or the modal proportions to actually assign a proper position to the specimen that you are considering. So this is a generic ternary diagram, okay? We have used simple letters A, B, and C, and these are the end member compositions. So if you are usually on this corner, you basically have 100% of B. If you are here, 100% of A, and here is the same, 100% of C. So what happens is that usually you look at the edges of the ternary diagram, and while you move away from a node, you lose percentages of that node. So that means that if I move my specimen here, This one is going to have 90% of B and 10% of A. The closer I get to A, the larger will be the percentage. So in this case, A is 90% and B it's only 10%. If you write in the middle, 50-50, 50% B, 50% A. Now, if we consider the internal lines, you can see that you have essentially three sets of lines. So from this spot in here, we have this line here and this other here. So usually this line refers to A. So it's essentially orthogonal to A, okay? So if I draw a line here, it's at 90 degrees with respect to these horizontal lines. The same is true for these other lines here. These ones have a relationship with B, and essentially they are the percentages of B. What about C? C has this initial line and then this one and this one. So again, they are orthogonal to a line that essentially bisects from this vertex C towards these other vertex and so on. So these lines can be counted and they will give you the percentages. So while you are inside the triangle, you can use those lines to recover the original percentage. How do you do that? Let's say we have 100% of B. This is the 90%. This line here will be 80%, 70%, 60%, 50% as I was discussing before, 40% of B, and this is your 30% of B, which is marked as 0.1 here. So the 0.1 is lying on the 30%. So that means that this specimen will have a composition that has partly B, and B value is 30%. What about C? We can count again. We have this is 90% C, 80, 70, 60, 50, 40, and 30% line for C, which is correct. And what's the last percentage? It's represented by these other lines orthogonal to A. So if we count from 90, we go down to 80, 70, 60, 50, and that's your 40% A. So as you see, by counting the percentages, we can place a point, and this corresponds to these initial compositions. Another interesting rule is if you sum up these values, they should return 100% because these are model proportions, so they close to 100. That's the idea. Okay, and if you sum this up, they will end up being 100%. Let's move on and look at another example. This time we use the proper terms, so we have an AQPF diagram, sorry, AQP diagram. And in this particular case, we have the alkali feldspar here, quartz here, and that's plagioclase. And we have a point here which has 40% quartz, 20% alkali feldspar, and 40% plagioclase. Okay, how do you plot that point? You count the lines again. So if we have 40% quartz, it's going to be 90. So remember, this is 100%, so that's 90. 90 goes to 80, 70, 60, 50, and 40. So the point has to lie on this line. But then we have to find out the 20% alkali feldspar, and so it's going to be the second line. So if this is the line in which I have 10% alkali feldspar, that's my 20% line. And so If that's the 40 and that's the 20, these are enough for me to place the point, and automatically I can check that it's correct because I get a 40%. Okay, so in this case, this is plagioclase, 100%, 90% here, 80, 70, 60, 50, and 40, and that's correct. So that's how you find the right spot for your specimen. If the rock is a little bit more complicated, so sometimes you have that more elements are reported, and since these are molar proportion, they will close to 100. So if you sum up this 20 plus 20 plus 40, which is the minerals that are of interest to you for this ternary diagram, you will realize they do not sum up to 100 because there are other minerals in this rock. And so since this has to close to 100, this QAP will result as less than 100. Exactly, it's less than 20. So you lose 20% basically. So how do you correct this problem? Because you need to produce actually a diagram that has proper percentages here to plot correctly the sample. So quite often you have to use a ratio here or a proportion that will essentially recalculate the values of these percentages for the three minerals of interest. So in this particular case, we have an example with essentially the fact that we have a total of 80%. So if we sum up these three, so the QAP will result in 80%. And so we need to correct this factor, so 20 will need, which represents the abundance of quartz and alkali feldspar, will need to increase to actually then sum up to 100. And so X will become 25 basically. So that can be calculated very quickly because you just need to essentially reorganize this equation. So you move this 100 on this side and you calculate the X. So you will have to do 20 divided by 8. So that's 0.4, I think. And then you have, no, 0.25, sorry. So that's 0.25. 2 divided by 8. We can do it very quickly as a check. Yes, it's 0.25. And choose, if you multiply that by 100, you get your 25. And that's your percentages for quartz and alkali feldspar. What about the calculation of the plagioclase? You have to put this 40 instead of this 20. So you get 40 divided by 80, which is, you know, instead of 0.25 is double than that, so it's going to be 0.5. And choose the result of X will be 50, and in fact it's correct, you got 50% here. Once you have recalculated these values so that they close to 100, so if you sum this up you get 100%, that's a check, so you're sure it's correct. So if this sum up to 100, you have done the right calculation, okay? So remember to use this formula to recalculate those values and so that they can close to 100, and that's because you need that they close to 100 to plot them correctly on this ternary diagram. Right, so now how do we plot these things? You will have to use this trick of having an intermediate imaginary line for the alkali feldspar, for example, because you have 25%, so it's right in the middle between the two lines. So we have a hatched line that represents the extra 5%. So let's repeat the procedure. So the alkali feldspar is here, and this line that is orthogonal represents 10% alkali feldspar. That's my 20% line for alkali feldspar. I add 5%, I go right in the middle, and I have marked this line which represents the alkali feldspar at 25%. But I don't know where my specimen is yet, I need another line. So let's use the quartz one. So this is 90% quartz, this is 80%, sorry, this is 10% quartz, this is 20%, and this is 25, right in the middle. So I draw this line and I find the location of my specimen. I can check it using the 50% line for the plagioclase. And I leave you to check this, but you can count and find it on your own. So why am I going to do all of this? Essentially to reiterate the fact that if you find then particular percentage ranges, let's say between 60 and 20, you will be in this domain of the thermal diagram, and so you can say that you have a granitic rock. So the purpose is really for the sake of classifying the rocks, and so you will essentially overlay this petrogenetic grid and call the samples according to the convention of the Strachan diagram. So for example, if the rock contains less than 20% quartz, and it does have quite a bit of alkali feldspar, let's say more than 70%, well, if that's the case, you are dealing with a cyanide. And this is the other step for the classification. You can get even more complicated cases in which you add subdivisions to these more general fields, and so you will be able to differentiate between a cyanogranite, a monsogranite, a granodiorite, and a tonalite. So remember, these percentages usually refer to the abundance of alkali versus plagioclase. So alkali feldspar. So that's your albites, and this is your anorthites, and yeah, it goes from 10%, so be careful that there is an error in here. This is 10%, and then you have 35% here, 65, 90, and you are left with essentially only plagioclase when you hit this corner here, which is the same as this one. So the only difference is the abundance of quartz, but in this particular case, these percentages are relative to really the amount of plagioclase versus K-feldspar. So I leave you with some examples here just for you to consider. So try to identify some of the minerals based on this lecture and on the specimen that were already presented, and try to give some proper names to these rocks. You could try to guess the percentages of mafics versus sialic minerals, and then try to plot these rocks into the ternary diagram so that you can put them in the right context for the name. The most challenging rock is this one. You will have to use the Strachan diagram for volcanic rocks for this one. These other three are all intrusive rocks. So good luck with this exercise, and I will see you again with the next lecture, which is lecture number 5, I think. And that one will be again a more general lecture that looks at a particular type of tectonic setting.